Yeah, so thanks for having me. Thanks for waking up. I tried to show up 5 minutes late to give everyone else 5 minutes. You can thank me later. Okay, so yeah, we'll talk about scaling exponents in stationary random graphs. Please interrupt, raise your hands if you have any questions or anything. What's the basic idea? We're going to think about just a graph G. So it could be, most of the time it's going to be infinite. It could be a finite graph. And we'll think about rooted graphs. So it'll be some fixed vertex, rho in V. And then let me tell you some kind of the geometric quantities that we're going to care about. Then I'll tell you the setting in which we're able to bound them, and then give some examples of in that setting, and then hopefully tell you some of the techniques that go into the proof. Okay, so I care about exponents related to various sort of quantities in the graph that scale as we take larger and larger snapshots of it. So a nice way to take a snapshot is to consider, let's say, a ball in the graph. So there's just a set of, so the ball of radius r around rho, just a set of vertices in the graph, such that the graph distance from rho to x is at most r. Here, that's just the shortest path distance on the graph. And okay, and then the first kind of exponent one might care about would be, say, like the exponent of volume growth. So I'm not going to define this formally yet. I'll define things formally in a moment. But we could think about this as just the way that the size of this ball scales as r goes to infinity. Okay, and the d sub f in the statistical physics literature is called the fractal dimension of the underlying graph. Okay, so this is I'm going to define a number of such quantities like this. I'm going to define them informally. Of course, what I mean is, well, I'll say more about what I mean in a second. But of course, this exponent doesn't necessarily have to exist. But if it exists, this is intuitively what I mean by it. Okay, so it's the rate at which the graph ball of radius r grows. Let's look at some more such exponents. Okay, so let's introduce the random walk. So this is just a simple random walk on the graph. Again, it's just that the graphs, all our graphs are locally finite, so you just choose a uniformly random neighbor at every step. And then once we have that, we can define the transition kernel in the standard way. And then another exponent one might consider is what's called the spectral dimension. So the spectral dimension, we don't have so many colors here. Let me just circle this exponent. The spectral dimension is the exponent that describes the scaling of this quantity, the probability that a random walk at 2n steps started at rho returns to rho, or is at rho at time 2n. And it's defined by this expression. Okay. As n goes to infinity. Okay, so there's two quantities. I'm going to define two more, and then I'll. Okay, so there's the fractal dimension, the spectral dimension. We can think about what's called the walk dimension. So we have the random walk. We have the graph metric. So we can define the walk dimension by, again, informally, just looking at the rate of growth of the speed of the walk, the rate at which we move away from the starting point. Okay. As n goes to infinity. So those are three dimensions: the walk dimension, the fractal dimension, and the spectral dimension. And then, what I'm going to write down in a second are the so-called Einstein relations, because the relation is expressed basically in the paper where Einstein introduces Brownian motion. And then one needs one more. Okay, so like one can think about this rate of volume growth as giving the density of some underlying medium, this is the rate at which a particle moves in the media. And then we'll need something about the conductivity of the underlying medium. So for that, we'll consider, again, in the graph G. So this is an annulus. There's a ball of radius r. There's the ball of radius 2r. And we'll consider the effective resistance across this annulus. Okay, so I'm going to assume people know what their effective resistance is. This is if I want to send, I'm going to use the effective resistance and also its dual characterization. But if I want to send 1 unit of flow, say from the r ball to the complement of the 2r ball, then the effective resistance is the minimum energy of such a flow, achieved by the flow with the minimum energy. Okay. And so then that's the last exponent, the resistance exponent. One might define in the following way. Okay, so this is in the graph G. We're going to look at the effective resistance between the ball of radius r and the complement of the ball of radius 2r, which notationally I'm going to write just this way. That's the complement. Okay, and this is zeta tilde. Okay, so zeta tilde because, well, in the statistical physics literature, if you just use zeta, that would correspond to the effect, the conductivity or the resistance exponent of the background medium. And then with the tilde, for instance, if we do percolation on the medium, then the tilde refers to that sort of the resulting graph G. Okay, so there's a bunch of exponents, and then here are some. I'll give these exponents meaning in a second. We'll talk about some explicit examples. But here are the so-called Einstein relationships that when things are sufficiently well conditioned, well set up, here are the relationships that one might expect to hold. That the speed of escape of the random walk is determined by the fractal dimension and this resistance exponent. And then the spectral dimension is given by twice the fractal dimension divided by the walk dimension. Okay. And I'll put little question marks here. These don't always hold in this, especially in the generality of the setting that I've done here. But I mean, I guess as a basic example, let's see if there's something with some contrast. As a basic example, I mean, one can consider what happens in if your graph is ZD, where there the dimension of volume growth is D. I know at least 2 of these exponents. The walk dimension is 2, right? The walk always moves at, here random walk moves at diffusive speed. That means that zeta has to be, I mean, these do hold there, so that would mean that zeta has to be 2 minus D, zeta tilde, and then the spectral dimension is D. Okay, so this is the setup. Now I want to prove these, in particular for some models I have in mind, like I'm going to prove a general theorem, but it's motivated by the desire to have these, by sort of not knowing what these values are for certain concrete models. So I mean, the most basic one is, for instance, if you do bond percolation in the square lattice at criticality, well, it's not known whether any of these exponents exist. But if they did exist, you could ask what they are. I guess, sort of work of Smirnov and Lawler, Werner, and Schrum shows that in the hexagonal lattice, at least this is equal to 91/48. But okay, well, like that's one example, concrete example where we don't know these values. And okay, so now I want to tell you about the setting where I want to be able to say something about them, and that's stationary random graphs. Okay, so let me tell you what a stationary random graph is. Okay, so now this over here, I didn't say it. You can't tell just by looking at it whether this is a random graph or not. But here, let's say the graph was fixed. Now I want to consider a random rooted graph. Okay, so this will be some random rooted graph. And then this is, let's make a definition. This is stationary. If the law, okay, so in general, unless stated otherwise, I'm going to start the random walk at the root of the graph. This random graph is a stationary random graph if the law is unchanged under one step of the random walk. And by law, we have to be specific what we're talking about here. This is law where I consider this object as a rooted graph up to isomorphism. Up to, in fact, rooted isomorphism. Okay. So what I mean is that the rooted isomorphism class, the distribution on rooted isomorphism classes are the same on both sides here. Okay, and in general, this is a really nice model for sort of stochastically homogeneous media. So like okay, so let's look at some examples of stationary random graphs. Okay, well, one would just be if we take any let's say a transitive graph with some fixed root, then this is a stationary random graph. Just because if I fix the graph at any root, then the two sides they're just law with an atom at this particular isomorphism class. That's maybe not so interesting, but another example would be just if we do the same thing. Let's say okay, well, this is a p bond percolation on this lattice, and here, of course, what I and this is the percolation cluster containing. Okay, let's just say I'm declaring this to be the percolation cluster containing 0. So I do independent critical bond, or not critical, just any bond percolation with some parameter p. I get some random subgraph. If I now take the cluster that contains the origin, then this is a stationary random graph. You can think about it. It's not so hard shouldn't be so hard to convince yourself that that this is true. Okay, so those are the two examples. There's another class of examples that are really nice, which come from taking Benjamini-Schrum limits. Alan talked about the Benjamini-Schrum topology yesterday, but let's okay. So this is one thing you can do. You can take so like a transitive graph, do bond percolation, do site percolation, you get stationary random graphs. Here's another way that you can get them. Let's take G sub n to be a family of finite graphs. And then we'll take rho sub n just to be a random vertex in a finite graph. Chosen from the stationary measure. Okay, so we take finite graphs, and for each graph we choose a random vertex according to the stationary measure. So just proportional. If they're unweighted graphs, just proportional to the degree. And then one can take a limit of such things in the let me write the Benjamini-Schrum topology, or the weak local topology. And I'll just say in words what this means. This means that this sequence of random rooted graphs converges in the Benjamini-Schrum topology to this random rooted graph. If it's the case that for every fixed radius, if I look at the law on balls of radius r in these graphs. So I take these balls of radius r. Again, these are finite subgraphs. I'm going to consider them only up to rooted isomorphism at the root rho sub n. And this entails, it's equivalent to the fact that for every r, the law on such graphs converges to the law of balls here. Okay. It's not really if and only if that is a definition, but okay. So in particular, like what? So for instance, I mean, if we look at the square lattice at criticality, like when p equals 1/2, we don't have an infinite cluster, but maybe you still want to sort of study it. So of course, Keston defined this incipient infinite cluster, and so one can consider the incipient infinite cluster as a stationary random graph in sort of the following way. You take basically take this graph with d equals 2 and p equals 1/2, and then condition on there being some, let's take this, this is I don't know, some box or some side length. Condition on there being a path from the origin to the boundary of this box of square r. This gives you now a this gives you a let's make the indices line up here. This will give you some graph, some random graph g sub n. Now choose not the origin here, but choose a vertex according to the stationary measure of this graph. Then you get a pair gn sub rho n. And now if you take the limit as n goes, right, again, this graph is conditioned on there being a path, an open path from the origin to the boundary of this box. Now if you take n going to infinity, this in fact, I shared, this in fact converges to the incipient infinite cluster in dimension 2. This is not how Keston defined it. Actually, this is from a later paper of Jirai, who showed that actually this retrieves the IIC. But this is another way of getting such graphs by taking limits, Benjamini-Strum limits of finite graphs. Okay, and then there's one other sort of like very prominent example. I mean, there's many, but another example here would be the UIPT. So that's the uniform infinite planar triangulation. Roughly speaking here, one can take G sub n to be a uniformly random triangulation of the two-sphere. When I say, okay, so you write down a list of all combinatorially distinct triangulations of the two-sphere. No one needs a picture, so I don't know why I'm drawing it. Triangulation. It's made from triangles. Okay. Again, choose a vertex rho n uniformly at random, and then this converges in the Benjamini-Strum topology to something called uniform infinite planar triangulation. This is not because this graph does not have uniformly bounded degrees. It's not even trivial. So that this limit that there's even a subsequential limit here. So one has to work a bit to establish this. I think this was done by Omer and Oded in 2003. Is that correct?
Yeah.
I'm caught. Oh, you did it before that, but that's.
Well, that's roughly correct. I don't
I mean, the important part is the year was the part which was possibly mistaken. That's.
It was years ago.
Yeah. Okay. 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 So good. So there's a rich family of such examples, and in fact, I mean, and like these, I'll mention it in the second. Okay. So let's define. Okay. So now we have the setting of station random graphs, and here are some examples. In all of these examples, in all of these examples except, okay, so I could give, I'll tell you about what happens for the IIC and D large in a moment. But in those cases, sort of now these relationships are established and we know exactly what these values are, except for, I mean, I only mentioned two things, I think, so it's weird to say that except for the one of them. I have more in my head, that's why. Right. Except for the IIC, these relationships are known and the quantities are known. But in particular, for every particular model, establishing these was a non-trivial task. Okay, yeah.
I know you may have said this briefly, but why shouldn't we expect those? Are you going to tell us why we should expect those relationships to happen in general, or do we have some good examples where they don't happen and understand why they don't happen?
We have all of those things. So, so it's okay. First of all, I haven't defined, what these things mean. So so I'll do that now in this setting. Yes, I would say that for, there's actually, so these two equalities are, in fact, 4 inequalities. And for 3 of them, there's a very intuitive explanation of what's going on. And for the 4th one, which is the one I'll tell you about establishing in a moment, it's less clear. But what your question is great. So make sure that I answer it. Okay. No, it's the correct question. What? Yeah. Yeah. I'll sketch it in a second. I just need to erase. I need to move a board over to have some more room. Yeah. Yeah, and in fact, it's depending on the sign, whether you're in the recurrent regime or the transient regime. Actually, the reasons for them to hold are a bit different. So I'll give you explanations that hold in the recurrent regime when this is greater than equal to 0. But like here, these hold even when this exponent is negative, and then the reason is less clear. And in fact, it's an open problem to establish that they hold in that setting, even under some quite it's under some natural generic assumptions. It's open whether they hold in that setting. So I would say that the transient regime is far less understood. In the recurrent regime, basically when you start the random walk in a ball of radius r, first of all you expect it essentially before it leaves this ball forever. Not forever. I just said the recurrent regime. So before it leaves, before it gets very far away from the r ball, you essentially expect it to fill up the entire r ball. And so that's why the speed of the walk would be determined by the volume, because it's going to visit everything inside this ball. But then the redundancy, the speed at which it fills it, it fills it up before it escapes to 2r is determined by this sort of the richness of paths in the graph, which is given by this resistance exponent. So at least intuitively, then it makes sense why, I guess you can think about it in a different way, which is that here, these two things are trading off, right? The speed of the walk is diffusive. You have a lot of volume, but which would take a long time to fill up, except that you also have a lot of connectivity. There's a lot of paths in RD. So I don't know if this answers your question informally, which is what I was trying to do. Like in the recurrent regime, you expect that you're going to spend, that you have to spend time r to the df time, in this ball, just because you will essentially touch every vertex at least once before you eventually escape the 2r ball. But then it could, but then every time you get here, you have a chance to get to the 2r ball, and this determines the number of chances. And of course, and then if you don't make it and you come back inside, then you're stuck to do this again, which means that the time it's going to take you to escape is something like the volume times the number of chances to go from the r to the 2r ball. So now you take the product of those two, and you get that it takes you about this much time before you escape the 2r ball. Did that make sense? Yeah. Okay. And then if you do actually the same exact calculation here under this model I just showed you, which is basically saying that essentially within this amount of time, I will expect to return to myself approximately as much as I would to a uniformly random vertex of this ball, then that's actually what gives this relation. Okay, because this one is about the return probability. So if I spend yeah, so like if it takes me if it takes me about this much time, sorry, if I should have written this. If I run the walk for n steps, then I will expect to be roughly, within a ball radius n to the 1 over this walk exponent. Now, so in a ball of that radius, I will see this many vertices. And now if I expect that at every time step, I'm returning to the starting point with probability that's roughly 1 over the number of vertices, then it says that, it says that my probability of getting there will be n to the minus df over dw. And if you look at this definition, it gives you this one. Okay, good. So now for stationary random graphs, let me define these. I don't really want to define them very carefully, but let me define what I mean by these exponents. Yes. Yes, I did. Keep going. Yeah. So okay. So yeah, I mentioned to you I'm context switching. I've been doing something very different for the last 3 months. So I've forgotten how to manage the whiteboards effectively, clearly, because but those things we'll remember. Okay, so in the setting of stationary random graphs, what do I mean formally by these exponents? Let me just tell you. Okay, so so now this is a random variable, and again, what I want to do is think about this random variable as being defined like this. Okay, which means that I want it to be that there exists a number d sub f such that almost surely df equals the limits up to sub-polynomial corrections. So almost surely over the choice of the graph and the random rooted graph, then this limit exists and is equal to some fixed number d sub f. That's what I mean. So this is not a random number, even though this is a random graph. What I mean by this, this is how I'm defining I'm defining this exponent existing if there exists a number d sub f such that almost surely this limit is equal to d sub f. Okay, and this is just a natural thing. You take logs, you get rid of these sub-polynomial corrections. Okay, so we have to be a little more careful with the walk exponent. Okay, so I'm just gonna, if you're on board with this notation, then that I just introduced, whatever, writing things this way, then to define the walk exponent, I would define it actually not like this, like this. Okay, this is some beta. The reason for defining it this way is because actually the walk exponent is usually defined differently. It's so this is the displacement from the origin after n steps, and you can also consider sometimes a dual characterization of it, which is like if I give you a radius r, how much time does it take you to escape the r ball? Okay. Okay, so so this is, let's say this is the first time such that xn is not in the ball of radius r, and then probably turns out it turns out that the definition for my purposes would have been the same, but it would have been quite strange to have not have T appear there. So great. Yeah, and then so you could define this similarly like, okay, so there's these two exponents which, if things are regular enough, you expect them to be equal. This is your displacement, your maximum displacement after n steps. This is the first time at which you escape the R ball. Okay, but in general, they can be different. And in fact, the existence of the two of them, Alan mentioned yesterday, like how, sort of like first moments and second moments. Here, actually, it's going to be a key that everything is done with first moments. But if you can, bet, like first, Alan said, first moments give you upper bounds, second moments give you lower bounds. Like here, these are nicely dual in the sense that first moment estimates for each of them, one first moment estimate gives you an upper bound, and the other first moment estimate gives you a lower bound. So in that sense, they're sort of both necessary. And then one more, we need the effective resistance exponent in this setting. So like if you look at this, by the way, you should object. I mean, Omer has unwittingly inspired some of these definitions because by objecting various times over the years. So you should object if you don't agree with anything. But I think this is the most natural setting, which is to consider sort of, for the exponents, like everything up to subpolynomial errors. Then with the effective resistance here, this becomes a little bit tricky. Now is the moment where I try to decide if I'm going to sweep something under the rug, and I am going to do it, so which means I shouldn't have told you. Okay, I'm going to allow a very strong definition here, which is that I'm going to allow sort of subpolynomial fluctuations in space. So this is in the, now this inner radius, I'll allow it that it can be, smaller by some subpolynomial factor. Okay, but the same idea. Okay, just look. Take this on. Take this at an intuitive level, and there's a concrete statement behind it. If you really like, the problem is that when you want to define all of these things, actually have a infinite lim sup associated to them. And for this one, for one side, you want to take the fluctuations here, but then you want it to be. But then for the other side, you want to take the fluctuations on, here, because. Please say it again.
Perhaps two.
Perhaps many things, yes. First of all, I guess it didn't matter so much because I took this, but yes. We should put a complement there, at least make it match up. And 2R. Yeah. I omitted the 2. The complement definitely should be there. I omitted the 2 because, okay. Because I didn't specify how the quantifiers fit in here, so I can't, maybe that means I'm allowed to hand wave over anything. But really what, of course, I said, it's a, okay, so for every delta, I can put R, I can look between R to the 1 minus delta and R. But yes, okay, so we have, good, so this defines a bunch of exponents. Now let me tell you some concrete models. Okay, so I'll leave the relations there. Okay, so since there was clamor for it, let's just so we can look at the at sort of G here as being, we can look at the IIC in dimension D for D large. D large, it means D bigger than 13 or D bigger than 11 if some expert knows better than I do. Large enough so that there are some lace expansion techniques that kick in and you can actually prove that something like the IIC exists. And there, okay, so there one has the Alexander-Orbach conjectures, which specify what these values should be. And for in the setting of D, which those conjectures are experimentally false for small d, but for D large, Gary Kozma and Asaf Nachmias established that they're true. And what did they show? So they proved in this setting that df equals 2, and that the resistance exponent equals 1. And then from this, okay, and then they concluded from this and these relations, I'll tell you how they had these relations in a second, that the walk dimension here is 3, and the spectral dimension is I heard 7 different numbers just now. The answer is 4 over 3, but does the math work? Does the math work out? 4, 3, perfect. Math is beautiful math. Yeah, okay. Here they got these numbers from work of Barlow, Jirai, Kumagai, and Slade, who established these Einstein relationships in a stronger setting called the the strongly recurrent setting. So okay, so let me in accordance with the informal nature of this talk, let me now. Okay, so here's a setting where this is non-trivial geometric information. I mean, this was a conjecture for a long time. It was hard to establish these things, and then from these relations, which were proved in a general setting. This implication is due to Barlow et al. You get these equalities. So let me prove. Okay, so let me state for you here a theorem I proved, and just so we can compare. So because what I'd like to be doing is giving you examples that the theorem applies to, but I haven't told you the statement of a theorem yet. So here's the statement of the theorem. If G is a stationary random graph, and df and the resistance exponent, this is okay. If those two things exist, in the sense that these limits exist, and by the way, and moreover that this resistance exponent is non-negative. So this is the recurrent regime. By the way, the recurrent regime does not entail recurrence. So for instance, like, I mean, there are examples where one is in the recurrent regime where the random walk is not recurrent, but that's what it's, okay. So if you have a stationary random graph and the growth exponent and the resistance exponent exists and is non-negative, then here's the theorem. Then those other exponents exist, and star holds where this is star. And I told you there's 2 definitions of the walk exponent, but those coincide. Okay. So that's the theorem, that in the setting of stationary random graphs, if you have control on the effective resistances and the rate of volume growth, then you get control on the random walk and the spectral dimension. And in fact, if you're really paying attention here, then you could come here and you can, not on this, but like on many of these things, you could take an annealed version where you say condition on the graph and look at the average value of these quantities. Everything collapses nicely in the case when these exist. All the quenched versions are equal to their annealed versions and so on. Okay, so here's a theorem, and in particular, this theorem applies in this setting. This is a stationary random graph. Okay, so the implication was known before, but this theorem, which is the main theorem I'm stating today, applies. Okay, so that's one example. Is there a clock in the room? Or Rick, you want to tell me what time it is? Okay. Wait, hold on. If I keep waiting, do I get 10 minutes? Did you have a question? Oh, you're just telling me. You're telling me what time it was. Oh, you were telling me I had 5 minutes left. It's like an auction. I had like the highest bidder. Okay, thank you. Okay, so yeah, so like another example here is the UIPT. So there, so the uniform infinite planar triangulation. Maybe this one is in 2003, Omar. Okay. So the yeah, so the rate of volume growth is r to the fourth, and then okay, then let's say, and additionally, okay, so this this is known, but okay, but I did have to sort of rederive it. So you know, this is basically a consequence of the Louisville quantum gravity theory. So Gwen Miller Sheffield, there's an important paper here of you know, there's 4 or 5 papers, Gwen Miller Sheffield or Miller Sheffield, Duplantier, Miller Sheffield's, you know, okay, and then also some very nice estimates of Ding and Gwyn in 2020, I guess that is a year, established that this holds. And then, yeah, okay, so this implies that the walk exponent here is equal to df, which is 4, and that the spectral dimension is equal to 2. And again, like this was something that actually took quite a long time. So, but when I say this implies, like the theorem I just stated implies that these things are true. Again, these took some, you know, actually this is a result of Yuan and Tom, that this is 4, that took quite a bit of work using, you know, using actually explicitly the structure of the couplings underlying this theory. And then, you know, and this spectral dimension bound was proved, one half of it by myself, the other half by Gwyn and Miller. Okay, like again, these are sort of, you know, each of these things was sort of like non-trivial to establish, and I'm just saying, so this theorem gives it to you from, again, from this basic information. And okay, because of the lack of time, let me just say that, like, okay, so for instance, this applies equally well to sort of the gamma LQG models for whatever it means, various kinds of like random triangulations and decorated in various ways, and or okay, things that couple to certain processes, blah blah blah. Okay, so the same thing applies. Let me mention one more thing that people might you know, might care about, which is the IIC in dimension 2. Here, none of these exponents are known to exist, but well, okay. At least this one, for the hexagonal lattice, one has, as I mentioned, Lalder, Werner Schramm, and Smirnov. Okay, at least this one holds for the hexagonal lattice, so we could say that we know its value if sort of you know, if conformal invariance holds. But it's not known what the resistance exponents are. But the estimates in the literature actually use these relations. So so I can tell you experimentally, this exponent has is the easiest to estimate. Okay, you get, actually there's one too many zeros there, if anyone was counting zeros. I don't know, you get something like this, and this, if you now use the Einstein relation there, then you get that the walk exponent is okay, plus or minus the same thing because it's a linear inequality. So like, I mean, this is what's listed on the Wikipedia page, and for instance, this theorem actually says that at least this arrow is formally true. So we don't know if this exists, but if it exists and it has this value, then this is the the correct estimate. So for instance, using this along with this relation just to get an empirical estimate for dW is a valid thing to do. Okay, good. So let me tell you one thing about the proof, and then we can consider this talk as an invitation to find me later if you want more information, which is the proof of this. All of the inequalities are relatively standard here, except for one, which is that which says that the walk doesn't go too fast. And actually, I prove this for any, not just in the non-negative setting. Okay, so this is the main inequality that's used there. That the rate of this says that the walk escapes sufficiently slowly. Okay, what you said there was a clock. There's the clock. Okay, so does that mean I have 4 minutes? Is that what the claim was? Okay, good. So let's see. How does one prove this? It's actually let's do it in 4 minutes. Okay. Okay, good. This board is getting a lot of use. Okay, so the idea here is to take a page from Riemannian geometry, or sort of conformal geometry, and remetrize the graph, to put a new metric on the graph. A new metric on the graph here will just be a length functional on edges, and it has to be compatible with a stationary structure in the sense that this is, for lack of time, you can ask, but that this is stationary. This is a stationary random graph with labels. Just means that erase the definition. Just means that when I take one step with a random walk, the law of the labeled graph also remains invariant. Okay. So here I'm metrizing the graph, and I'm going to assume. So consider the class of all length functionals I could put on the edges. Again, they have to be compatible with the stationary structure, and they have to have unit area in this sense. Okay. So again, I didn't say why, but the reason stationary random graphs are nice is because you essentially get to do geometry that feels compact. So for instance, I can average. This is like a really nice thing. So I'm in the nice, comfortable space of doing like analysis on a compact space, even though it's an infinite graph. Okay, so if I have this, then here's a theorem which says that if I consider the speed of the random walk now, not under the graph metric, but under the graph metric, just take the path metric where these are the edge weights. And I look then at the displacement of the random walk, and let's say I square it. Then basically, under any such change of metric on the graph, the speed of the random walk is at most diffusive. Okay, so here's a fact. Okay, this is formally only true if G has sub-exponential growth, which is fine for us because we're assuming that it has almost sure sub-exponential growth. We're assuming it's only interesting if we have polynomial growth. Okay, so this is so this uses Markov type theory. I don't have time to go into it, but it says that if I put a different metric on the graph, then I can say that the random walk doesn't leave its starting point too fast. Okay, so if you take the square over the other side here, you see maybe it just looks more familiar. Okay, at most diffusive speed, and so what it means is, like if I want to prove, so here I'm showing you the random walk goes slowly. To prove this inequality, I want to show that it goes, that the random walk escapes even slower. And so there's a natural thing to try and do, which is to find a metric on the graph that's of this form that's asymptotically bigger than the graph metric. The goal would be to say that I can find a let's say that this thing scales like the graph metric to a power. Okay, so some like where alpha is bigger than 0. And I'm going to stop in 30 seconds. Right? And just to see that this intuitively works out, if I know that the walk has the most diffusive speed in this metric, and this metric is bigger than the graph metric, then I know that the speed in the graph metric goes even slower. So this is now the whole game, to find such a metric where, which is bigger than the graph metric by a power. Okay, again, it's subject to some area constraint, which is why this is like a non-trivial thing. And this is where the effective resistance comes in. There's a dual characterization of the effective resistance, which says that the effective resistance across this annuli, like in our setting, is given by the conformal width of the annuli. So I look over all length functionals on the edges in the annulus that have energy at most 1. And I try to maximize the width. And if I do that, then the width actually is the effective resistance, which in our setting is r to this power of zeta. And now what you can imagine is that what this gives me a way to do is like with some relatively cheap length functional, I can stretch out this, I can put these lengths on the edges and I stretch out the space. Because if the effective resistance is large, it means that the distance from here to here becomes large. That's just the characterization of the effective resistance by the conformal modulus. And okay, so now wave your hands a little bit. The point is like this is clearly giving you some kind of control like this. So now let's say let's just finish with the picture here. Just you just do a Poisson process of annuli in your space at various scales. And then use the length functional, coming from each of those annuli to endow the edges with some length. And what you'll do is simultaneously stretch out the metric at all scales to achieve this. So that's so if you wanted, this is quite analogous to a procedure of it's analogous. It doesn't really have much technically in common. Maybe it does. To a procedure of Keith and Laxo, who showed that sort of the conformal dimension of a metric measure space is only attained if conformal. Okay. Conformal dimension means the dimension under is only attained if if you know something about the conformal modulus of annuli in that space. I'm going to conclude here now. But yes, so the effective resistance gives you a way of basically stretching out the space at every scale. You get a new metric on the graph that's bigger than the graph metric by power, and then you use this fact, which is coming from Markov type theory, to bound the rate of escape in the changed metric, and it gives you an even better rate of escape in the graph metric. Okay, so that's the whole argument. What's the main open question here? The main open question is what happens when this exponent is less than 0. And this is a huge open question. There's something called the resistance conjecture of Gregorian, Hu, and Lau, which just knowing all of these things is not enough in that setting. You also need you at least need a Poincare inequality, which tells you that between every pair of points in the space, there's a sufficiently sort of rich family of curves. But even in that setting, under those assumptions, it's unknown. This is a giant open question. It would be beautiful to make any progress on the transient case. Okay, let me stop there. Thank you.